Hi, this is the first of 3 lectures describing how the 3 main requirements on the operating range of an electric drive influence the size and the cost of the drive. We start by analyzing how the required maximum torque influences the size and the cost of the electric machine. The torque produced by an electric machine is equal to the total tangential force F created on the outer surface of the rotor, multiplied with the rotor radius r. The currents and the magnetic flux density create a shear stress on the rotor surface, measured in Newton per square meter. The shear stress is proportional to the magnetic flux density B and to the linear current density J in ampere per meter of rotor circumference. In most electric machines for vehicle propulsion, the size of the magnetic flux density and the linear current density are typically maximized to what the magnetic materials and the cooling of the windings can allow for. This means it's difficult to increase the shear stress for a given type of machine and given size. Instead, we can approximate it as a constant. So if the maximum torque of the machine must increase, that increase will not come from the increased shear stress. The total tangential force on the rotor is the shear stress times the air gap area of the rotor. Now we can derive the total torque. It's the shear stress times 2 pi times radius squared times the length. Since the shear stress was approximately constant, the size of the machine needs to be increased when more torque is required. We can see that the torque of the machine is equal to the volume of the rotor times twice the shear stress, so the volume of the machine is proportional to the torque of the machine. The cost for materials and the machining of the parts will be roughly proportional to the volume of the machine. Since the torque of the machine is also proportional to volume, this means that the cost is roughly proportional to the torque of the machine. If the machine is made significantly bigger, we can also expect the linear current density to be increased, and therefore the cost may increase a little less than linearly with the torque of the machine. Again, this is of course a simplified analysis, but we can expect the cost for an electric machine of a given type to be roughly proportional to the maximum torque. Now we will see how the maximum torque of the electric machine is interpreted in terms of the operating region. Do you think this operating region looks odd? Well, that is because this model has no field weakening range, but is capable of producing maximum torque up to its maximum speed. Here the maximum torque is 100 Newton meter and the maximum speed 5000 RPM. Here the max torque is 200 Newton meter and here 300. When we consider different maximum torques like this, the size of the machine will have to be increased proportionally, and so will the cost. In this lecture we have shown that an increase in the required maximum torque will lead to increased size of the electric machine and a cost which increases roughly linear to the required torque. Thank you for listening.